Hello learners, and welcome to practice exam number 3. For practice exam number 3, and of course for exam number 3, we are going to be focused on chapters 14, 15, and 16. You will be given 20 questions, and you'll have 1.5 hours to complete this exam. Just like every other exam, we want to have goals. We want to make sure we completed all lectures, the homework, and for every single type of homework problem, and for any of the practice problems, you want to make sure you have a strategy and approach. And this is going to come from practice and review. What does an approach mean? It means that when I see a question, I'm not just using my anxiety to help me kind of get overwhelmed. I'm breaking it apart piece by piece, even word by word if necessary. And you're going to repeat this process of completing the lectures, doing the homework, creating a strategy. And for question number 1, it says, calculate delta G naught of the reaction using the following information. So automatically it's telling me about delta G naught of the reaction. I'm automatically getting my brain and my wheels are spinning, and I'm thinking chapter 16 information. And so I know that this question and the question beyond are going to be chapter 16 information. This is one way you can organize yourself when you're studying. Get all your notes now for chapter 16. If you had any areas you did not understand, you want to make sure you go back and review before you try to approach this particular problem. Let's continue on. It says circle your answer, and it gives us this reaction. 4HNO3 gas plus 5N2H4 liquid is going to produce 7N2 gas plus 12H2O liquid. They give us delta H naught of formation and S naught values. And so because they give us both these values and they want us to get delta G naught, I know that I can use my delta G naught is equal to delta H naught minus temperature times delta S naught equation. And here's that equation here. Now we know if we want to utilize this equation, we have to make sure that all of our variables are in the correct units. So for S naught, the units are joules per mole Kelvin, and so we want to make sure we convert that to kilojoules per mole Kelvin. Also, for temperature, we're at 298 Kelvin because we're at standard condition. And then finally, if we want to go ahead and get our values for delta H naught and delta S naught, we must find a delta H naught of the reaction and delta S naught of the reaction. And that's going to equal to the sum of the moles of products multiplied by their delta H of formation values minus the sum of the moles of reactants multiplied by their delta H naught of formation values. And of course, for delta S naught of the reaction is going to be the sum of the moles of the products of S naught, of course, multiplied by their S naught values, minus the sum of the reactants multiplied by their S naught value. So let's go ahead and get these two numbers, and then we'll go ahead and take our delta S naught of the reaction and convert it to kilojoules per mole Kelvin. Once we have both of our values, and we already have our temperature, we can go ahead and plug them in and solve for delta G naught, which is what this question is looking for. All right, so our delta H naught of the reaction, that's what I'm going to start with. I'm going to focus on my products and subtract them by my reactants. So I'm starting with 12 times negative 285.8. I'm getting it directly from the table. I'm going to add that to 7 times 0 because there's a 7 in front of the N2 here and a 12 in front of the H2O. Next, I'm going to subtract that by 4 times negative 133.9. I'm going to add that to 5 times 50.6. Again, these numbers are because of the coefficients that come before the substances. Of course, what I do is get all these numbers in my calculator and I kind of write them tiny above whatever I have. So when I multiply this number together, I get negative 3429.6. 7 times 0 is 0. 4 times negative 133.9 is negative 535.6. And then 5 times 50.6 is 253. I then am going to sum these numbers together, and I get negative 3429.6. When I add these two numbers together, I get negative 282.6. So of course I have to take my negative 3429.6 and subtract it from negative 282.6. And I get negative 3,147 kilojoules per mole because I'm dealing with delta H naught of the reaction. Next, I'm going to focus on delta S naught of the reaction. That's going to equal to 12 times now this bottom portion of the table, which are my S naught values. And so that's going to be 12 times 70.0. I get 840 from that. Then I'm going to add that to 7 times 191.6, and I get 1341.2. I'm going to subtract that from 4 times 266.9, and I get 1067.6. And then finally, I'm going to add that to 5 times 121.2. When I multiply that, I get 606. This is where a lot of folks end up having a lot of mistakes because they end up either mixing up these values and they don't take their time with calculations. I take my time with this. If I were you, this will be some of the questions I start with first so I can take as much time as I need and I lower my stress. All right. Once I have my values, I'm going to go ahead and sum these two together, and I get 2181.2. I'm going to subtract it by the sum of these two numbers, which is 1673.6. When I subtract these two numbers, I get 507.6 joules per mole Kelvin. Of course, we know we have to take our delta S naught units, or say our delta S naught of the reaction units, and put them into kilojoules per mole Kelvin. And so we're going to divide by 1,000. When I divide by 1,000, I get 0.5076 kilojoules per mole Kelvin. Now let's go ahead and solve for delta G by plugging in all of our values into this expression. So delta G is going to equal to negative 3147 kilojoules per mole minus 298 times 0.5076 kilojoules per mole Kelvin. Again, we're at 298 Kelvin because we're at standard conditions. When I multiply these two numbers together, I get 151.2648 kilojoules per mole. So now I have to go ahead and subtract both of these numbers. I'm going to take minus 3147 and subtract it by 151.26848. I get negative 3298.2648 kilojoules per mole. Now, of course, this is a large number, and I have to go off of the significant figures that are given to me. The smallest number here is going to be 1, but we're not going to look at 0 here. We're going to go with 3, which is 70.0 here, and 50.6. So with three significant figures, I will write negative 3.30 times 10 to the 3 kilojoules per mole as my answer for number 1. So you have to stop yourself and say, what is going to be my approach when I see this? Number 1, if you don't understand what delta G naught of the reaction is, if you can't write notes down for yourself at this point, you need to go back to the lecture material and rework that information from it. Okay? If you don't remember the delta H naught and delta S naught, then of course you're going to have to memorize those summing of that, which is very similar to Chem 101 information. Delta H naught of the reaction is exactly from Chem 101. So you're just layering information by adding delta S naught of the reaction. Okay, folks? Again, produce whatever strategy you want. Take your time with this one. Make sure your units are correct and make sure that your calculations are correct because it's easy to mix up these table values. Let's get on to question number 2. Question number 2 states, calculate delta G of the reaction. Well. There is no degree sign, so we know we're not at standard conditions. So therefore, we have to use the delta G of the reaction expression when we're at non-standard conditions, okay? So they say calculate delta G of the reaction, at 298 Kelvin under the conditions shown below for the following reaction. They gave us 3O2 gas forming 2O3 gas. They gave us a delta G naught of plus 326 kilojoules. They also gave us a partial pressure of O2 at 0.41 atmosphere and a partial pressure of O3 at 5.2 atmospheres. So we want to make sure that we're gathering information and getting all the expressions necessary to be able to answer this question. We need our non-standard condition delta G, and of course, we need to be able to utilize any of the other information that's given to us. All right, so first, the non-standard delta G of the reaction expression. So we have delta G is equal to delta G naught plus RT natural log of Q. We're using Q because we're not at equilibrium. So what is Q? Q is going to equal to the partial pressures of the product divided by the partial pressure of the reaction. Why am I talking about partial pressures of products and reactants? It's because we're already given partial pressures. So again, we're thinking of equilibrium when it comes to pressure versus equilibrium when it comes to concentration. Next, we have temperature, which we already know is 298 Kelvin. We have the universal gas constant, 8.314 joules per mole Kelvin. And then, of course, our delta G naught value was given at plus 326 Kelvin. Okay? Let me go ahead and write that plus sign a little bit better. Now, first things first, if we want to be able to use this expression, we have to make sure we have the correct unit. When I'm thinking of all my units, I'm like, wait a minute, I see my kilojoules for my delta G naught, and I see my units of R is going to be 8.314 joules per mole, and of course, Kelvin's going to cancel. In my answer, though, everything's in kilojoules. So instead of converting my delta G to joules, I'm going to now take my R value, or universal gas constant, and convert that to kilojoules. So I take 8.314 and divide it by 1,000. When I do that, I get 8.314 times 10 to the negative 3 kilojoules per mole Kelvin. Now I can go ahead and use my universal gas constant expression, or universal gas constant value into this expression. All right, next we have to go ahead and get our Q value. We're already given partial pressures of our reactant and our product. So our partial pressure of O3 is going to be squared because there's a 2 in front of it. And we're going to divide by the partial pressure of O2, which is going to be cubed because there's a 3 in front of this one. Okay? Now we're going to plug in our values that are given. So we have 5.2 atmospheres is a partial pressure of O3. We're going to raise that to a power of 2. We're going to divide that by 0.41 atmosphere, which is the partial pressure of O2. And we're going to raise that to a power of 3. Next, our Q of pressure is going to equal to 27.04 divided by 0.068921. When I divide these two numbers, I get 392.333. Okay, folks? Now, of course, because I already know I have to take the natural log of Q, I go ahead and take the natural log up front. It's just a strategy that's going to make it easier for you as we're going along. So the natural log of QP is going to equal to the natural log of 392.333. And that equals 5.972111609. Now that I have all my values, all that's left to do is plug and chug. Let's go ahead and get it. So my delta G is going to equal to 326 plus 8.314 times 10 to the negative 3 multiplied by 298 multiplied by 5.972111609. And so when I multiply all these numbers together, I get 14.7963365 kilojoules. And I'm going to add that to 326. So overall, I get 340.7963365 kilojoules. Now, how many significant figures do we have? Well, technically, as you can see, we do have 2 significant figures if we're going off of partial pressures, but our answer choices have 3. So we're basically going to write 3 significant figures because that is what our answer choices have. So our answer is going to be 341 kilojoules, or letter A. Question number 3 states, determine the equilibrium constant for the following reaction at 498 Kelvin. So they're asking for equilibrium constant, which is going to be K. They give us a temperature of 498 Kelvin. They tell us to circle our answer. They give us a reaction of 2 Hg gas plus O2 gas is going to form 2 H2O solid. They give us a delta H naught value of negative 304.2 kilojoules and a delta S naught of negative 414.2 joules per Kelvin. So they're asking us about equilibrium, and they're giving us delta H and delta S, which we just saw in question number 2 is related to delta G naught. So the question is, what expression is going to relate our K to delta G naught? Well, the expression that's going to relate the K is going to be delta G naught, which is equal to RT, negative RT, natural log of K. All right, so let's go ahead and put this all together and get ourselves a bit organized. Now, of course, I'm talking to myself. So delta G naught is equal to delta H naught minus T delta S naught. And if we already have these values for delta H naught and delta S naught, we can solve for delta G naught. All right, now how are we going to verify and connect delta G naught to our equilibrium constant? Well, there is an expression. Delta G naught is equal to negative RT, natural log of K. So we can basically use this expression to solve for natural log of K, which is negative delta G naught divided by RT. And of course, once we get this expression, we can take the natural log of both sides and solve for the K value. And that is exactly what we're going to do for this question. And that's the strategy you want to approach for this type of question. You want to make sure you're just piecing together every little part and saying, what does this go with? What does this go with? That is a way to start making sure you're breaking things down. All right, so let's go ahead and start getting our values. Number 1, it's all about having the same units. Otherwise, we can't use any of these expressions. So for delta G naught here, we want to make sure that our delta H naught and delta S naught are in the same units. As you can see, we need to make sure that we do kilojoules per Kelvin here for delta S naught. And for delta G naught, if we're going to use this expression here, we might want to take our universal gas constant and convert that to kilojoules as well. That way we can go ahead and leave our delta G naught value that we find here up top, just leave it alone. So let's go ahead and get started. First, let's go ahead and solve for delta G naught. Again, we have to make sure everything is in the same units. So I go ahead and convert my delta S naught from joules per Kelvin by dividing it by 1,000, and then of course getting kilojoules per Kelvin. So I'm going to take negative 404.2 and divide by 1,000 to get negative 0.4142 kilojoules per Kelvin. So now I can go ahead and plug in all my values into my expression. My delta H naught is negative 304.2. I'm going to subtract that by my temperature, which is 498, and multiply that by my negative 0.4142 delta S naught value. When I multiply 498 times negative 0.4142, I get negative 206.2716 kilojoules. I'm going to take that number, and of course, I'm going to be subtracting it from my delta H naught number. So when I take negative 304.2 and subtracted by negative 206.2716, I get negative 97.9284, which is my delta G naught value. The goal is to solve for our equilibrium constant. So we have to move forward and take our delta G naught value and use it in our new expression here. Now, this expression can be rearranged again to solve for natural log of K. I already have my delta G naught value, and I already have my temperature, which is given. For my R value, this is where I need to take my R value from joules per mole Kelvin to kilojoules per mole Kelvin. So I'm going to take 8.314 joules per mole Kelvin and divide by 1,000. That's going to give me 8.314 times 10 to the negative 3 kilojoules per mole Kelvin. Now I can go ahead and use this expression. So natural log of K is going to equal to negative G naught, delta G naught divided by RT. That's going to be negative times negative 97.9284 kilojoules, which is our delta G naught value, divided by 8.314 times 10 to the negative 3, which is going to be multiplied by 498 Kelvin. So when I multiply these two numbers together, I get 4.140372. I'm going to divide this number, right, 97.928 by the 4.140372. When I divide these, I get 23.652077764. And this is what natural log of K is equal to. Now, of course, I have to solve for K. So I have to take the natural log of both sides. When I do that, I'm able to isolate the variable K by itself. And because I'm able to isolate it, I can actually solve for it. So I'm going to get K is equal to E raised to a power of 23.652077764. When I do this in my calculator, I get K is equal to 1.87 times 10 to the 10. And this is my final answer here. Now, of course, as far as significant figures, I should have 3 based on the temperature, and I do have 3 here. So everything looks good. Let's move on to question number 4. All right, question number 4 says, calculate delta S naught of the reaction for the following reaction. They say that the S naught for each species is shown below. So meaning they're giving you that standard state value. All right, we have C2H2 plus H2 gas is going to form C2H4. The S naught values are shown here, and they just want us to calculate delta S naught of the reaction. So again, use a strategy. If we've already calculated delta S naught of the reaction for previous questions like we've seen before, then all we need to do is go back and flip that page and be like, hey, what did I do here? So that's going to be a way to look at this question as a freebie. So we know that delta S naught of the reaction is equal to the sum of the products times their S naught values minus the sum of the reactants times their S naught values. So all we need to do is use this to our advantage. We've seen this before again, and just plug in the values, and that's pretty much it here. So first we have our one product and we have 2 reactants. So this is going to be 1 times 219.3 subtracted by 1 times 200.9 plus 1 times 130.7. So when I go ahead and get the sum of these values, it's just going to be 200.9 plus 130.7, which is equal to 331.6. I'm going to take 219.3 subtracted by 331.6, and I get negative 112.3 joules per Kelvin. So that is letter C. Again, this one is a quick, quote-unquote, freebie type of question. And I just want to make sure that it's very, very clear. Some folks are only relying on this video to think they're going to get through. Please understand that I'm trying to show you as many different variations of these problems as possible. But if you only rely on the practice exam, you are not studying this information. Okay? And if you're given something different on the real exam, then you're going to become overwhelmed and you're going to become confused. So instead of, to alleviate all that, just stop and actually study the material. That way, and not only just studying the material, go ahead and get an approach from the material. Because that way, when I see any type of questions that I'm just like, I've seen this before, but maybe not in this variation, then I can start mapping things out for myself. But if I only memorize what I see in the practice exam, then that's not going to be helpful to you. Okay, folks, so just keep that in mind as well. Now, with questions like this, where it's very specific and you're using a specific equation, it's really going to be based off of whether or not you remember it and know how to use it, right? And of course, you know how to match units and things like that. But for some questions, you want to make sure that you can manipulate the variables in any way possible, even outside of what's given in the practice exam. And that means that you have to review your homework. You can go further and look at textbook exercises and also go back and review what you see in the lecture material. Question number 5 states, above what temperature does the following reaction become non-spontaneous? They give us 2H2S plus 3O2 is going to form 2SO2 plus 2H2O. They also give us a delta H value of negative 1036 kilojoules and a delta S value of negative 153.2 joules per Kelvin. So because this question is asking about a temperature or above what particular temperature does the reaction become non-spontaneous, they're asking you for the crossover temperature. So remember, for a crossover temperature, we're really looking at our T delta S value. So what we're going to do is take our T delta S value and create a straight line for it. And of course, when it comes to delta H, that's going to be constant across the system, whether it's endothermic or exothermic. Wherever these two lines cross is going to be our crossover temperature. Okay, that means above this temperature or below this temperature, we could have spontaneity. But we can't say which one is going to be above and below until we look at the signs of delta H and delta S. So spontaneity is going to depend on these signs. For delta H, we see that we have a negative sign, and for delta S, we see that we have a negative sign. And remember, we were given the table to help us understand the delta G value or spontaneity. So if delta H is negative and delta S is negative, then our negative T delta S value and our overall delta G is equal to delta H minus T delta S expression, or the Gibbs free energy change expression. That's going to end up being positive. So therefore, delta G is going to be based on temperature. It's going to be spontaneous at low temperatures when both these values are negative, and it's going to be non-spontaneous at high temperatures when both of these values are negative. So when we're looking at our overall graph here, and they're asking us, hey, above what temperature does the following reaction become non-spontaneous? They're already telling us non-spontaneous because they know we're dealing with two negative delta H and delta S signs, okay? So that means whenever we go ahead and calculate our crossover temperature, above that temperature is going to be non-spontaneous, and of course below that temperature is going to be spontaneous. Okay? Now it's all from us understanding that both these signs are both negative. So what we need to do is simply just calculate our crossover temperature, and that is going to be setting delta G equal to 0 at equilibrium, so we can get rid of that expression, and therefore we can rearrange this to solve for a T. So our crossover temperature is going to equal to our delta H divided by our delta S. So this is our expression to solve for our crossover temperature. Okay, folks? Now, we have to make sure our units are the same in order to use this expression. So again, our delta H is good, so that's going to be negative 1,036 kilojoules, but we have to change our delta S to kilojoules per Kelvin. So let's go ahead and do that. So I'm going to take my delta S value that's given, and I'm going to divide it by 1,000 joules. I get negative 0.1532 kilojoules per Kelvin. So I'm going to take this value and put it into my expression. So now my crossover temperature is equal to negative 1,036 kilojoules divided by negative 0.153 kilojoules per Kelvin. I get 6.762 times 10 to the 3 Kelvin, which is going to be letter A. So for number 6, it states, which change is likely to be accompanied by the greatest increase in entropy? So we know entropy is going to be capital F. They're talking about the greatest increase in entropy. And we know there were like different things that could influence, or different factors that could influence entropy. You know, microstates. So if we increase the microstates, of course, we can increase the entropy. We also talked about temperature. We also talked about going from solid to liquid to gaseous phases. We also talked about dissolution, or, you know, dissolving in solid. We also talked about atomic size and complexity. So we're going to use this and all these different factors to help us answer this question. So what we're going to do is go from letter A through D, and we're going to see if we have an increase or a decrease in entropy. If we have an increase in entropy, then of course we are going to look at that particular letter and then see if we have any other increases. If we do have more than one increase, then we have to look at which one will be the greatest between the two. So let's go ahead and get it. Letter A, you have N2 gas plus 3 H2 gas molecules is going down to 2 NH3 gas molecules. Since they're all in the same phase, what are we going to do? All we can do is really just count here and talk about the number of microstates. Because we have 4 molecules here and only 2 molecules here, when we go from reactions to products, we're actually going to be decreasing entropy. So we can have something that's going to have the greatest increase if it's decreasing. So letter A is totally out. Again, I didn't have to really use any of my factors. I went straight off of microstates. Increase microstates, increase entropy. Because we're going down to from 4 gas molecules down to 2, that's definitely a decrease in entropy, because we don't have, we've decreased the number of molecules as well. Now for letter B, we have Ag plus aqueous plus Cl minus aqueous is going to form Ag solid. We're going from aqueous or liquid solution to a solid precipitate. So we are effectively decreasing our entropy. How do we know that? Well, we can go off of this factor, which is phase change. If you're going from solid to liquid, you are definitely going to be increasing entropy, but if you go from liquid to solid, you're going to be decreasing your entropy. For letter C, you have CO2 solid is going to be forming CO2 gas. So this is definitely a situation where we are increasing entropy. Again, based off of phase change. If we're going from a solid to a gas, we're increasing entropy as we go from solid to liquid and liquid to gas. So letter C is the contender. Let's look at letter D. We have H2O gas is going down to H3O liquid. Again, we're talking about a phase change. We're going from a gas down to a liquid. So we are decreasing our entropy. So they're asking us which change is likely to be accompanied by the greatest entropy. We definitely are going to choose letter C. Now, some folks will just memorize a couple of these factors. If you're studying for the exam, you need to know all the factors because you could be given a lot of different ways of these reactions. And again, it might not be as simple as the one you see here. So this is a perfect example of sometimes not only relying on the practice exam to get through. All right, let's continue on. Okay, so for question number 7, it says, what is the molar solubility? Automatically stop. If we're talking about molar solubility, that means we are in chapter 15 material now, folks. So go ahead and gather up all your chapter 15 lecture notes. You want to gather up any homework problems that you're going to review. Use it all to help you as you're going along. Okay? Again, that is basically what you want to do. And so you can always organize yourself and say, okay, well, the first 6 questions were chapter 16. Now we're moving on to our chapter 15 portion. And when we get to chapter 14, you'll be able to organize further. Again, organizing, compartmentalizing is going to help you because there's so many chapters to deal with. And the chapters are chunky, right? So again, take your time with organizing. This says, what is the molar solubility? Now, what is molar solubility? Solubility is usually going to be in grams per liter. So molar solubility is just going to be in moles per liter, okay? Of AgCl. If we're talking about the molar solubility of AgCl, that means that this AgCl is a solid. Why? Because the solubility is related to KSP. Remember, we are dealing with chapter 15, so now we're talking about the solubility product ion constant, and that's going to be equilibrium of solubility-based solutions at this point, okay? So it's telling us what is the molar solubility of AgCl, which is a solid, that's going to be in 0.40 molar NaCN solution. So I kind of visualize it. So I'm like, let me write a beaker. I know it's going to have AgCl, and I know that's going to be a solid, right? And I need to figure out the molar solubility of this solid, which we'll talk about as we go along. Now, if I take NaCN and put it in solution, it's going to disassociate. It disassociates into Na plus and Cn minus. Now, based off our understanding of acids and bases, we know that Na plus is a part of a strong base, so it does not react with anything. It is basically a spectator ion, okay? That means we only really can focus on Cn minus when we're thinking about everything as we go along with our calculation, okay? So I now have in my beaker AgCl, and then I have Na plus and Cn minus floating around. How much of each? 0.40 molar. Now let's continue on. They're telling us if this whole entire solution is going to be in 0.40 molar NaCN if the colorless complex ion also forms. So wait a minute. Not only do we have AgCl, and that's molar solubility, it's going to be mixed with this overall salt solution that disassociates into Na plus and Cn minus. They're also telling us that a complex ion forms, which is AgCN2 minus. Now, if a complex ion forms, guess what? We now can layer in another piece of information, which is Kf, or the equilibrium constant or formation. And this is how we're able to now connect two concepts together, Ksp for solubility and formation constant for forming a complex ion. Now, if you're going to be taking these two concepts and bringing them together, that means you're going to be coupling them. If you're coupling them together, that means the product of Ksp multiplied by Kf is going to give us an overall K value. So let's go ahead and stop and break everything into pieces. First, we need to consolidate what Ksp is. Anytime I'm given Ksp, I know I need two things. I need the Ksp expression, and I need a dissolution equation, meaning showing how AgCl is going to dissolve into its individual ion. Now, if I'm also given Kf, or Kf a formation value, I know I'm not going to need a Kf expression, and I'm going to need a formation equation, okay, to show how I actually can form this AgCN2 minus. So these are the first two things that we definitely want to go ahead and get. So first, I get my Ksp expression. So KSP of AgCl is going to be based on its ions. Again, AgCl is a solid, so it's not going to be involved in our expression. So therefore, we just have Ag plus and Cl minus, which is what happens when we disassociate AgCl. And this expression is equal to 1.8 times 10 to the negative 10, which is given. I can also have my dissolution equation here, which is AgCl solid, which is going to dissolve in equilibrium to form Ag plus and Cl minus. And then next, for my Kf value, or my formation constant of AgCN2 minus, that expression is going to be the product divided by the reactant. So let's go ahead and get our formation equation. When you're getting formation equation, start off with the products. I go ahead and write AgCN2 minus, and then I go ahead and break these apart. I know that this is a polyatomic ion, and I know this is Ag plus. So I'm going to take my Ag plus and write it as one of my reactants. And then I have 2 of the polyatomic ion of cyanide here, so I'm going to put 2 for Cn minus. All right, folks, and that is how I form my formation equation. Now, this formation equation is going to have a Kf expression where you take your products, or AgCN2 minus, and divide it by your reactants, which is Ag plus, and then Cn raised to a power of 2. This entire expression is equal to 1.0 times 10 to the 21. Now, the next thing we want to do is couple the expressions. That means we're going to add both of these reactions together. We're going to get rid of things that are the same on both sides, like Ag plus, and now we'll be able to bring down an overall equation. So AgCl solid plus 2Cn minus is in equilibrium to form AgCN2 minus plus Cl minus. And this overall reaction is now going to have its own overall equilibrium constant, which is going to be K, which is equal to multiplying your KFP value times your Kf value. So overall K is going to equal to 1.8 times 10 to the negative 10 multiplied by 1.0 times 10 to the 21. When I multiply these two numbers together, I get 1.8 times 10 to the 11. So this is now my K value for my overall expression. Why is this important? Because they want the molar solubility. And it would have been easy if we only had to use KSP. But because we had to mix it and then we end up forming a complex ion, of course, everything got more complex. So now we have to use our overall equation to solve for molar solubility. AgCl is not going to help us. 2Cn minus is not going to help us because that's not a part of AgCl. The complex ion is not going to help us. So Cl minus is what we need to solve for in order to get molar solubility. How can we know that this is true? Well, we can look at the KSP expression for AgCl. We see that Cl minus is one of the actual concentrations. If we find this, because it's only 1 mole, then we can automatically find the molar solubility of AgCl. How do we do that? We need to set up a Rice table. If we set up a Rice table with this new overall equation, using our new overall K expression, we can solve for X. Once we solve for X, we automatically are going to get the molar solubility. So let's go ahead and do it. All right, so I'm going to go ahead and set up my Rice table with my new overall expression. AgCl solid plus 2Cn minus in equilibrium to form the complex ion plus Cl minus. Again, our solids we don't have to deal with for our Rice table, so we're going to plug in the values that we had. We already know that our Cn minus is going to be 0.40 molar. So we go ahead and add that as initial amount, minus 2x because we have a 2 in front of our Cn minus, and then we have an equilibrium expression of 0.40 molar minus 2x. Next, again, we're going to fill out the rest of our Rice table, and we get X values and X values for our complex ion and Cl minus. Therefore, once we solve for X, we automatically are going to solve for Cl minus concentration, which is going to be equal to the molar solubility, which is what the question asks for, right? So I can go ahead and say that my overall K is equal to 1.8 times 10 to the 11. That's going to equal to X squared, or X times X here. And that's going to be divided by 0.40 molar minus 2X squared. Since this is an overall K value, we are not going to be dealing with assumptions here. So since we have our 0.40 molar minus 2x squared, and we also have x squared here, we can take the perfect squares, which means we can take the square root of both sides. So I'm going to take the square root of this expression on this side and take the square root of our K expression here. All right, so when I take the square root, I get 424264.0687 is equal to x divided by 0.40 molar minus 2x. So of course I have to cross multiply. I'm going to take this ginormous number and multiply by 0.40. I'm also going to take this number and multiply by 2. And what I get is that this entire expression is going to equal to x. So I'm going to have my x is equal to 169,705.6275 which is what you get when you take this number multiplied by 0.40 and subtracted by 848,528.1374, which is going to be the number that you get when you multiply this number by 2. And then, of course, x is going to be left over. Now, the goal is to isolate x so we can solve it. So I'm going to add 848,528.1374x to the other side. I get 848,529.1374x is equal to 169,705.6275. Again, there is a 1 in front of the x here. So that's the reason why we have to add it, add a 1 to this ginormous number here. Now that I have this expression, I can go ahead and isolate x by dividing by 848,529.1374. So when I go ahead and do that, and I divide the number, I can solve for x. So in my calculator, I have 169,705.6275 divided by 848,529.1374. My x value is going to equal to 0.1999. My significant figure should be 2. So my x is equal to 0.20 molarity. Now, this x is equal to the concentration of Cl- at equilibrium, which is also going to be equal to the molar solubility of AgCl. So x is going to equal to our answer, which again is 0.20 molar. This is a very long question, but if you break it down, you figure out exactly what all these little portions mean, and you layer it together, you can find an answer. And if anything else fails, the goal is you write as much work as you possibly can to at least try to get partial credit. Let's move on to number 8. Number 8 says calculate the pH. So boom, we're talking pH. Yes, in chapter 15, it's a long range of information, right? We just talked about solubility stuff for chapter 15. Now we're getting into pH information for chapter 15. And for that information, we related it to buffers. So it says calculate the pH of a buffer. And if we're talking about the pH of a buffer, we know we can automatically use the Henderson-Hasselbalch equation, which is pH is equal to pKa plus the log of the conjugate base divided by the weak acid. Now they're telling us to calculate the pH of a buffer that is 0.225 molar of this weak acetic acid and 0.162 molar of this overall salt solution. So when I go ahead and disassociate this, I'm going to get K plus and the acetate ion. If I dissociate my weak acid, I get H plus and the acetate ion. So as you can see, even though this is a salt solution, our K plus is spectator, so we actually have the conjugate base of our weak acid, which is going to make sense because when we're trying to create a buffer, we must have a weak acid and its conjugate base or a weak base and its conjugate acid. Here we have a weak acid, and we're actually adding here its conjugate base as well. Okay, folks? So they then go on to tell us that the Ka for this weak acid is 1.8 times 10 to the negative 5. So let's go ahead and make some consolidations here. For this question, it's like, okay, well, the pKa, what is pKa? pKa is going to equal to the negative log of the Ka value. We already have the Ka value, so we can go ahead and get this number. Now, what is our conjugate base? Our conjugate base, we already said, is going to be the acetate ion here, and that's already going to be 0.162 molar. So we can go ahead and use that here. For our weak acid, that concentration is given as 0.225 molar. So all we need to do is calculate pKa, which is negative log of 1.8 times 10 to the negative 5. When I put this in my calculator, I'm going to get 4.7447274749.5. So that is my pKa value. Now all I have to do is put it all together. So filling in my expression, my Henderson-Hasselbalch expression, pH is going to equal to pKa, which is 4.7447274749.5, plus the log of the conjugate base, which is 0.162 molar, divided by the weak acid, which is 0.225 molar. That means I'm going to have 4.744 plus the log of 0.72. Of course, that's just me dividing 0.162 divided by 0.225. All right, folks? Again, now we're going to have our 4.744727495 and add it to our negative 0.142667504. We get a pH value of 4.60. And so 4.60 is going to be letter E for our overall question. So for question 9, it states a solution contains 0.021 molar Cl- ions and 0.017 molar I- ions. So what I did is just created a solution. I have a beaker here. and I just have a fake solution, and I have my 0.021 molar Cl minus floating around, and my 0.017 molar I minus floating around. Okay, then it says a solution containing copper 1 ions is added to selectively precipitate one of the ions. So if I'm adding copper 1 plus, okay, or copper plus ion, okay, then that means I'm going to be precipitating either CuCl or CuI. And selective precipitation just means that we're separating these ions based on their solubility. So when it comes to solubility, we're asking a couple questions. We're saying, okay, the one that has the lower KSP value tends to be the one that's going to be precipitate out of the solution first. Also, the one that produces the lower Cu plus concentration when we actually get our mass of our KSP expression is also going to be the one that usually precipitates out of the solution first. For this question, they want to know at what concentration of copper plus ion will a precipitate begin to form? Another way to rearrange that question would be saying, okay, well, if we want to figure out what concentration of Cu plus ions a precipitate is going to begin to form, we need to figure out which ion is going to precipitate first. And that's going to be based on whether or not it has a low KSP value and a low Cu plus concentration. So first, let's look at KSP values. We already know we're going to be forming CuCl or CuI. The KSP value for CuCl is equal to 1.0 times 10 to the negative 6. The KSP value for CuI is going to equal to 5.1 times 10 to the negative 12. So automatically KSP is winning the race as far as which one's going to precipitate first because it has the lower KSP value. We now have to do calculations to figure out which one has the lower Cu plus concentration. Now, in order to do that, we need to do a couple things. Anytime you see KSP, just like anytime you see Kf or any kind of equilibrium expression, you want to make sure that you write the expression. And of course, you want to make sure that you actually write the dissolution equation as well, since we're focused on KSP. So let's go ahead and do that for both of them. Go ahead and get our expressions for KSP, and then we can visually see how easy it is to now solve for the Cu plus concentration to be able to answer this question. And of course, after we figure that out, they just want to know what the identity of the precipitate is. So basically we get the concentration, and then we choose whether the identity is going to be CuCl or CuI. All right, let's start with our KSP for CuCl. So the expression is going to be Cu plus multiplied by Cl minus, all based on the reaction for dissolution like we see here. So we're starting off with the solid. It's going to dissolve into the individual ions. Solids don't matter for us in our expression, so that's how we only have the ions here. Now, as you can see, this calls out the Cu plus ion. So we can go ahead and solve for it. Cu plus concentration is equal to the KSP value divided by the concentration of Cl minus. We already know the KSP value. We already know the concentration of Cl minus. So we divide these two numbers. 1.0 times 10 to the negative 6 divided by what's given as 0.021 molar of Cl minus. I get 4.76 times 10 to the negative 5 molar. Next, we're going to focus on the KSP of CuI. This is going to equal to the concentration of Cu plus times the concentration of I minus. All based on the expression or the dissolution equation, CuI solid is going to dissolve into equilibrium, dissolve at equilibrium into its individual ions of Cu plus and I minus. Okay, folks? Again, we can go ahead and solve for Cu plus concentration, which is going to equal to KSP divided by the I minus concentration. That's going to equal to 5.1 times 10 to the negative 12 divided by what's given, which is 0.017 molar. This is equal to 3.0 times 10 to the negative 10 molar. So we have to go back to what our answers are for this overall question. They said at what concentration of copper 1 ion will a precipitate begin to form? That concentration is going to be the lowest concentration, which is going to be 3.0 times 10 to the negative 10 molarity. Next, it says what is the identity of the precipitate? The identity of the precipitate is going to be CuI, or copper 1 iodide here, which is going to be CuI solid and 3.0 times 10 to the negative 10 molar to answer both of our questions there. And I've kind of boxed them around and circled it here, so it's just easier for you to call them out. Let's move on to question number 10. Question number 10 states, determine the molar solubility of FeOH2 in pure water. They give us the KSP value for FeOH2 is equal to 4.87 times 10 to the negative 17. So molar solubility has to do with KSP. It has to do with being able to disassociate that solid into its individual ions. So if we see a KSP value, let's go ahead and get an expression and an overall equation. So we're going to take our KSP of FeOH2 and we're going to disassociate it into its ions, which is going to be Fe2 plus and OH minus. Now, based on our dissolution equation, our expression is going to be the concentration of Fe2 plus multiplied by the concentration of OH minus squared, folks. And this entire thing is equal to 4.87 times 10 to the negative 17. So looking at our overall dissolution equation, what can we do? We can go ahead and solve for the molar solubility if we set up a Rice table. Now, when we set up a Rice table, we're going to be solving for X, and whatever ion that we land on, which is going to be Fe2 plus, for example, and it only is simply going to be X, we know that's going to directly equal the molar solubility of FeOH2. Why? Because there's only 1 mole of it. And when there's 1 mole, you can directly relate it to molar solubility. If there's more than 1 mole, like we see here with OH minus, then we would have to take the amount of X that we have and multiply it by 2. So therefore, our molar solubility will be based on Fe2 plus. So I'm going to go ahead and set up my Rice table. Again, because FeOH2 is a solid, we do not have to use it in our Rice table. That means we're only going to be left with the products or our ions. So the products initial amount are going to be 0. This is going to be plus X because there's only 1 in front of it. This is going to be plus 2X because there is a 2 in front of the OH minus. And therefore, our equilibrium amounts for Fe2 plus is X, and for OH minus is going to be 2X, which is why the molar solubility is going to be simply X, or the Fe2 plus concentration. Now we take our KSP expression, which is going to equal to 4.87 times 10 to the negative 17, and also equal to our X times our 2X squared, okay? Again, just plugging in our values that we have here. Now, what we need to do is consolidate our variables here. We're going to have 4.87 times 10 to the negative 17. We're going to have X, and then this 2 is going to square this 2 here, so it's going to be X times 4, and then this 2 is going to be squaring the X here, so 4 squared. Again, we're still going to have 4.87 times 10 to the negative 17 on this side, but now, since we have X multiplied by X, we can add them together. So 2 plus 1 is going to be 3, and we're going to have 4X cubed here. All right, so I got the 4.87 times 10 to the negative 17 is equal to 4X cubed. I have to divide by 4 to isolate X by itself, and I get, when I divide 4.87 times 10 to the negative 17 divided by 4, I actually get 1.2175 times 10 to the negative 17. Now, to get X by itself, I have to take the cube root, so I can get rid of cubed on this side, and I need to take the cube root of this number here. So the cube root of 1.2175 times 10 to the negative 17 is going to equal 2.30 times 10 to the negative 6 molar. Now again, this is going to equal to our Fe2 plus concentration, which is equal to our molar solubility. So that is letter E. So for number 11, it says a solution containing CaCl2 is mixed with a solution containing Li2C2O4. So I automatically go ahead and get my beaker. I'm going to mix both of these solutions. Of course, when they're mixing together, they're going to disassociate into their individual ions. So instead of CaCl2, I'll have Ca2 plus and 2Cl minus. Instead of Li2C2O4, I'm going to have 2Li plus and C2O4 2 minus polyatomic ions hanging out in solution. They're saying this solution is going to be mixed to form a solution that is 2.1 times 10 to the negative 5 molar in calcium ion and 4.75 times 10 to the negative 5 molar in oxalate ion. And then they want to know what will happen once these solutions are mixed. They also give us an equilibrium constant, or the KSP value, of CaC2O4 as 2.3 times 10 to the negative 9. So I'm going to take what's given to me, I'm going to mix them together, and the question they're really asking me is, will this solution become saturated at equilibrium, unsaturated and produce ions only, or supersaturated and produce a precipitate? And the only way to figure this out is to compare our Q and K values. Of course, if Q is going to be less than K, then we're definitely going to be going towards our products. And if Q is going to be greater than K, then of course we're going to be going towards our reactants. If Q is equal to K, we are at equilibrium. So what we need to do is take our KSP value, which is already given, 2.3 times 10 to the negative 9, and we can move forward with that. We need to get our QSP value, okay? So at QSP, just means our reaction quotient at solubility as well, okay? We're going to have our concentrations, which is going to be Ca2 plus, multiplied by C2O4 2 minus. And so we're already given these values as they were already given in the overall question. All we need to do is plug them into the overall QSP expression. And so I'm going to get 2.1 times 10 to the negative 5 molar multiplied by 4.75 times 10 to the negative 5 molar. I get 9.975 times 10 to the negative 10. So this is my Q value. My KSP value is 2.3 times 10 to the negative 9. So my Q value is actually going to be less than my K value. And when Q is less than K, we're going to be going towards the overall product. And so folks might say, wait a minute, where is our overall equation going to be? Where's our dissolution equation going to be? Or where's going to be our equation to help us figure this out? Well, I forgot to write it. So here is our CaC2O4, which we know is a solid based on the fact that they gave us a KSP value. We're going to just dissolve this into Ca2 plus and C2O4 2 minus ions. All right, folks? And that's how we're able to get our QSP value. And of course, that's how they also got the KSP value, by using this overall reaction and getting these expressions. So when we're saying Q is less than K, that means that we're going to be going towards products mostly, and we're going to be building an unsaturated solution. So all we need to do is go forward with this information and answer the questions or the letter choices as we see here, whether or not they're true or false. So letter A, a precipitate will form since Q is greater than KSP. We know that's not true, so we can move on from that. They want to know what will happen once these solutions mix. We already compared our Q and K. We found that there's less, so we're definitely dealing with something that's going to be ions only or going towards product. Letter B, nothing will happen since both calcium chloride and lithium oxalate are soluble compounds. We're not actually using these compounds. We used them to start with, but we didn't use them to end with. For letter C, nothing will happen since calcium oxalate is extremely soluble. That doesn't make any sense. They're both going to dissolve. They're both going to be soluble ions. Letter D, nothing will happen since KSP is greater than Q for all possible precipitates. Well. If Q is less than K, that means that K is greater than Q. So yes, we can definitely check out letter D as a possible contender. And letter E, there's not enough information to determine. Well, we can't say there's not enough information to determine because we already know Q is less than K. So automatically, I will choose letter D as my answer choice. Nothing's going to happen here because our Q value is smaller than K, or we can say our K value is greater than Q. And in that scenario, what's going to happen is we're going to be going towards our product. Our products are ions. So there's not going to be in precipitates or anything like that. We're dealing with ions only in solution. For question 12, it says the solubility of BaCO3 is 7.9 times 10 to the negative 3 grams per liter. Calculate the solubility product, KSP, ignoring hydrolysis. What it means by ignoring hydrolysis is basically ignoring any, or we don't consider any of our ions reacting with water. That's what we're trying to say, okay? Now, this is the molecular weight of BaCO3, which is 197 grams per mole. So again, I see solubility, I see KSP. I would definitely want to get a KSP expression, dissolution equation. I definitely want to write details about solubility. Like, for example, this is solubility, but if we want to get the molar solubility, it would have to be moles per liter. Why would we want to get the molar solubility? Well, because if we're dealing with KSP, we know that we're dealing with concentrations at equilibrium. So we need to be able to take our solubility and get molar solubility using what's given. All right, so I want to go ahead and get a KSP expression and a dissolution equation. So, of course, I'm going to dissolve my solid BaCO3 into its ions, which is Ba2 plus and CO3 2 minus. Of course, this is going to be in equilibrium. My KSP expression, therefore, is going to be the concentration of Ba2 plus multiplied by the concentration of CO3 2 minus. Now, we need to solve for my KSP value. So I need to use the solubility that's given to solve for molar solubility and get my concentrations of my ions. Now, the solubility that's given is in grams per liter, so I need to convert it to moles per liter. I'm starting with 7.9 times 10 to the negative 3 grams per liter, and I'm going to multiply by the molar mass given. So that's going to be moles divided by 197 grams. When I take 7.9 times 10 to the negative 3 and divide it by 197, I get 4.0 times 10 to the negative 5 molarity. This is equal to the molar solubility of barium carbonate, okay? And so the molar solubility has to do with number of moles of ions. We have 1 mole of Ba2 plus, and we have 1 mole of CO3 2 minus. So both concentrations are equal to 4.0 times 10 to the negative 5 molar. All we need to do now is basically use these values and put them back into our KSP expression and solve for KSP. So I'm going to put my KSP value as 4.0 times 10 to the negative 5 molar multiplied by 4.0 times 10 to the negative 5 molar. And I get 1.6 times 10 to the negative 9. That is going to be letter B. For number 13, it says, assume that the standardized aqueous solutions of each of these are available. They give us a substance, and then they give us the ionization constant. So for this substance, NaOAC, it has a Kb value. For RNH3 plus Cl minus, it has a Ka value. For RNH2, it has a Kb value. And for HOAC, it has a Ka value. Automatically telling you which ones are acids and which ones are bases. Kb has to do with weak bases. Ka have to do with weak acids. All right. The question says a buffer with the desired pH is 5.0 would be conveniently prepared by appropriate mixtures of what? So they're taking what are the substances we know from this table, and they're going to put them into mixtures for letters A through D. Now they're telling us we want a buffer with the desired pH is 5.0. So we have to start asking ourselves some details about what buffers are, what information we can get about trying to figure out the pH when we're making a buffer and apply it to what we see here. First, we have to ask ourselves, what is a buffer? A buffer is going to be a weak acid and a conjugate base, or a weak base and a conjugate acid. So when we're looking at all of these pairs, we can go through and figure out which one's a base, which one's an acid, and see if they actually have the combination of weak acid and conjugate base. If they don't, we can automatically eliminate it. Also go off of pH. So they want us to get a pH of 5.0, right? And so we know that in order for us to get the proper pH, it's going to be a range based on the buffer that we create. So pH is equal to about plus or minus 1 away from the pKa. So if our pH is equal to 5, then minus 5 is going to be 4, and minus 1 is going to be 4, and plus 1 is going to be 6. So we can also look for pKa values that are between 4.0 to 6.0. But if we're looking for pKa values, that means we have to look for Ka values here based on what's given. And then finally, we also can use the Henderson-Hasselbalch equation, which states that pH is equal to pKa plus the log of A minus divided by HA. And this all is going to depend on the amount of information that you are given. Now, I can tell you straight up that we can basically use our information or conceptual portion of this by just understanding what a buffer is. And we probably will be able to get away with the pH is equal to pKa plus or minus 1. Because if we find out what our weak acid and conjugate base is, or if we found out what our weak base and conjugate acid is, we can simply just go ahead and use the Ka value and see if it's between 4 and 6. So that's going to be two ways we can approach it. And you might have to mix both of these ways if you cannot decide between the answer twos. So let's start with letter D. We're starting with HOAC, which based on the table we know is a weak acid. And we're going to mix that with RNH2. So RNH2 is going to be a weak base. So far, sounds good. But remember, a buffer needs a weak acid and that weak acid's conjugate base, not just some random base. So if I'm looking at my acid here, the conjugate base of this acid, we have H plus and we're going to have OAC minus. So the conjugate base is actually OAC minus, not RNH2. So that's actually not even going to follow the buffer rule. Let's go with letter C. We're going to have a buffer mixed with a base mixed with another base. How do I know they're bases? Look at my table. This is Kb value, this is the base. Now we know Na plus is spectator, so it's going to be OAC minus, that's going to be the base here, okay? And then it already tells us that RNH2 is also a base. So I can get rid of that just by using just my understanding of buffer. Next we have HOAC and water. Again, we know this is going to be an acid here. And so sure, water can act as a base because it's amphoteric. But when we're talking about a buffer, we need the conjugate base of this overall acid. So letter B is not going to work. Automatically, we're down to letter A, which has to be the answer choice by process of elimination. Let's verify it. We have NaOAC, which we know is simply going to be OAC minus, and then we have HOAC, which we know is going to break down to H plus and OAC minus. So we effectively have an acid and we have its conjugate base. So because we have an acid and its conjugate base, and specifically this is a weak acid, we can use letter A as a pair to create a buffer. And of course, we'll go through the process of creating a buffer, and then we will get it to its desired pH of 5.0. So for this question, the best approach would just be knowing basic information about buffers. Now, if you were trying to go ahead and figure out the pH based on the pKa values and trying to get a range between 4.0 to 6.0, it's easy when it comes to the ones that already give you a Ka value. So if I get the pKa of this, pKa is simply going to be the negative log of whatever your Ka value is. So for this one, I get a Ka value of 4.74. Now you might be saying, okay, 4.74 is going to work. But remember, the goal is to create a buffer solution, not just a solution of this substance. So we definitely would need its conjugate base in order to be able to use this expression. So this really won't work based on what's given. Again, in order to use this to help us figure out a pKa range that we can verify for our buffer, we need the conjugate base and weak acid ratio. So if I'm just looking at these Ka values, it won't work out. Let's move on to question number 14. All right, question number 14 states, what is the hydronium ion concentration? I'm automatically going to write H3O plus of a 0.300 molar acetic acid solution with the Ka value of 1.8 times 10 to the negative 5. The equation for the dissociation of acetic acid is CH3CO2H plus water is going to be in equilibrium to form H3O plus the acetate ion, or its conjugate base. Now, automatically, just by knowing that I have a Ka value in a weak acid, I know I'm dealing with chapter 14 information. So you want to stop and you want to make sure you're going to get chapter 14 lecture material notes. You want to make sure you're going to go get chapter 14 homework material or any notes you're using to help you get through this information. Now, since they want a hydronium ion concentration and they already give us the concentration of this weak acid, how do I know this is a weak acid? Because it's not one of my strong acids. That's one way to kind of easily be able to answer that question, okay? Another reason why is because they gave me a Ka value. A Ka value is usually going to be dealing with weak acids or weak bases if you have a Kb value. So if I have a Ka value, I have to make sure I have a Ka expression. So the Ka expression is going to be based on my products and my reactants. So it's going to be my H3O plus concentration multiplied by my acetate ion here, divided by my acetic acid. All right, so that is my Ka expression, and this entire expression is equal to 1.8 times 10 to the negative 5. We can go further, of course, and we can look at an overall reaction that's given, and because they want us to solve for the H3O plus concentration, and they give us a Ka value, we know we can use a Rice table for this. So if I use a Rice table for this, all of my H2O liquid doesn't matter to us, and all I need to do is plug in the values that's given. They already give us 0.300 molar for acetic acid. It's going to be 0 for my initial amounts for my products, plus X for my products, minus X for my reactant. I have 0.300 molar minus X here, and then I have X and X here. Now, looking at my K value that's given, it is 1.8 times 10 to the negative 5, so I can make an assumption with this. Therefore, my Ka value, okay, this looks like a Q. Sorry about that. That's definitely an A. So my Ka value is going to equal to 1.8 times 10 to the negative 5, which is going to equal to X times X divided by 0.300 molar. Of course, this X times X is just simply going to be X squared, okay? So I normally just rewrite it as X squared here. Now to solve for X, which is going to be our hydronium ion concentration, which is what they want, we're going to cross multiply these two numbers. When I multiply these two numbers, I get 5.4 times 10 to the negative 6. So to solve for X or isolate X, I'm going to take the square root of both sides, and therefore my X is equal to 2.32 times 10 to the negative 3 molar. And that X value is equal to my hydronium ion concentration at equilibrium. Now, of course, I do have 3 significant figures here. I'm going off of the acetic acid concentration they gave me, but because they gave us a Ka value that has a lower number of significant figures, this also could be 2.3 times 10 to the negative 3 molar. Okay, folks? So that'll be the two answers I will accept for this, which are basically the same thing. Let's go ahead and go to question number 15. Question number 15 states, what is the pH of a 0.60 molar pyridine solution that has a Kb value of 1.9 times 10 to the negative 9? They're asking us for pH, and they're giving us a base dissociation constant. That means we have to find a way to relate pH to pOH, which we know is going to be pH is equal to 14.00 minus our pOH value. And if we have a pOH value, that means we're definitely going to have to get a pOH expression. And from this pOH expression, we know that we need the concentration of OH minus. So if we find the concentration of OH minus, we can go backwards and find pH. Now they gave us a Kb value, so that means we're going to have the conjugate acid, okay? We're also going to have OH minus divided by the base, and that is the expression that we have for Kb. What else can we add here, folks? I mean, you can add as much information as you want as far as notes to approach this problem. It gives us the equation for the dissociation of pyridine already. So usually when I see a Kb value, I'm like, what's my expression? I already have my expression that I'm going to specifically tailor to the reaction given, but I already know how to set it up. And again, they already wrote the reaction for me, so I don't have to come up with it myself. This is pyridine. It's going to be mixed with water. It's going to produce C5H5NH plus and OH minus. Okay, folks? So we're starting off with a base, and it's going to create a conjugate acid and OH minus in solution. So what can we do? We can set up a Rice table here. And if we set up a Rice table here and we get our equilibrium amounts, we can solve for OH minus concentration. And we solve for the OH minus concentration, we can go ahead and solve for pH. All right, I went ahead and set up my Rice table and filled it out. So they want to know the pH of a 0.60 molar pyridine solution. So that's going to be the initial amount I have for pyridine. Water doesn't matter to us. And then our initial amounts for our products is going to be 0. So our product amounts for equilibrium are simply going to be X. And for our reactant is going to be minus X here for the change, and then 0.6 molar minus X. Now, our Kb value is 1.9 times 10 to the negative 9. It is small enough for us to be able to make an assumption, so we can get rid of the minus X here. Now, let's go ahead and write out our Kb expression. We have the C5H5NH plus multiplied by the OH minus concentration divided by C5H5N. This is going to equal to X times X divided by 0.60 molar, which is equal to the Kb value of 1.9 times 10 to the negative 9. So essentially, I have X squared divided by 0.60 molar, which is equal to 1.9 times 10 to the negative 9. I'm going to cross multiply these two numbers, and I get 1.14 times 10 to the negative 9. Of course, to solve for X, I'm going to take the square root of both sides, and I get X is equal to 3.376 times 10 to the negative 5. And I know that X value is going to equal to my OH minus concentration. Now that I have my OH minus concentration, I'm going to automatically solve for POH and then pH. So POH is equal to the negative log of the OH minus concentration, which we just solved for 3.376 times 10 to the negative 5. When I take the negative log of this number, I get 4.4715 Now, in order to find the pH, I'm going to take 14.00 minus my POH value. So that's 14.00 minus the 4.4715 value, and I get pH is equal to 9.53. So when it comes to bases, yes, there is a little bit of an extra step because you're dealing with OH minus concentration, but you're still able to get that pH. So for this answer, I would circle letter C. Let's go on to number 16. Now, number 16 says, determine the H3O plus concentration in a 0.265 molar HClO solution. So automatically you have to ask yourself, is this a weak acid? Is this a weak base? What is it? You should automatically know this is a weak acid. Why? Because it's not one of our strong acids. Now let's move on. It also gives us a Ka value that's verifying that this is a weak acid. It says the Ka of HClO is 2.9 times 10 to the negative 8. Circle your answer. They just want us to determine the H3O plus concentration. Since we're given a Ka value, we must come up with an expression. All right, folks? That expression is going to help us disassociate an acid. So let's go ahead and write our dissociation of an acid expression, our reaction itself, and then write our Ka expression too. All right, so I have my weak acid, and it's going to dissociate into its individual ions of H plus and ClO minus. You could have also written this as taking your HClO, which is your weak acid, and mixing it with water, okay? And so you're going to end up getting H3O plus and ClO minus. Both of these things are saying the same thing because the concentration of H plus is synonymous with the concentration of H3O plus, right, folks? So all we need to do now is solve for X, which is going to help us solve for H3O plus. So in order to do that, we need to set up a Rice table, fill out our Rice table amount, and then move from there. All right, so from our Rice table, here's my reaction. I mean, I could have used this one here. It's going to give me the same information. Now, initial, I have 0.265 molar that's given for my weak acid solution. For my products, they're going to be initially at 0. Now, again, the change is going to be minus X. It's only going to be 1 in front of HClO and plus X for my overall product. Therefore, equilibrium, I'm going to have 0.265 minus X. And as you can see, I got rid of minus X because my Ka value is small enough, so I can make that assumption there. Now, my product equilibrium amounts are simply going to be X. So I'm going to fill this out into my Ka expression, and I get x squared divided by 0.265 molar is equal to 2.9 times 10 to the negative 8. I then move forward and cross multiply, and I get 7.685 times 10 to the negative 9. Now to solve for x and isolate it, I have to take the square root of x squared. So when I take the square root of x squared, I have to take the square root of the other side, and therefore x is equal to 8.8 times 10 to the negative 5 molar. And this x value is equal to the H3O plus concentration. And so that will be my actual answer here. Now I have two significant figures based on the value that's given, so yes, it will be 8.8 times 10 to the negative 5 molar here. For number 17, it states a solution with the hydroxide ion concentration. Automatically, I'm going to write OH minus concentration here, and it tells me that it has a hydroxide ion concentration of 4.15 times 10 to the negative 7 molar is what? Right? So they want us to know basically whether or not this solution is going to be acidic or basic. Since we're given the OH minus concentration, we can go ahead and get the POH, and we can use the POH to figure out the pH. Depending on the pH value, we can say whether or not it's acidic or basic. You also can use the POH value, but of course, that's not a scale we normally use. So for some folks, you might not have remembered it that way. All right, so once we figure out that portion of the question, it then says, and has a hydrogen ion concentration of what? So then they want to say, once we know whether or not the solution is basic, what's the hydrogen ion concentration? So we definitely have to go and try to figure out all the relationships we can between OH minus, H3O plus, and pH. Let's go ahead and get it done. All right, so again, we have our OH minus. We can go ahead and solve for POH. Once we have our POH, we can solve for pH. Once we have our pH, we'll figure out if it's acidic or basic. So I took my OH minus concentration, which is 4.15 times 10 to the negative 7, and I took the negative log of that number. I got a POH of 6.381951903. To get pH, I took 14.00 minus my POH value, and I got 7.618. Because we are above 7, this solution is going to be basic. So automatically, I can get rid of letter E, I can get rid of letter B, and letter A. Now I'm down to C or D. So of course, I have to do the second part. So this part is basic here. The second part is, what is the hydrogen ion concentration? Well, we know that OH minus multiplied by H3O plus is equal to the KW value. So I can rearrange this expression to solve for H3O plus. So again, it's going to be H3O plus is equal to my KW divided by my OH minus. You can also say just ion product of water, which we know is always going to be 1.0 times 10 to the negative 14. I'm going to divide that by my OH minus concentration, which is 4.15 times 10 to the negative 7 molar. And when I divide these two numbers, I get 2.41 times 10 to the negative 8 molarity. Therefore, my answer choice is going to be letter D. Number 18 states, calculate the pH, which we're used to seeing by now, of a 0.400 molar KBRO solution. So if we're talking about a solution of KBRO, we know it's going to disassociate into K plus and BRO minus. So of the two, K plus is spectator and BRO minus has the ability to be going forward as a base or be used as a base, okay? What kind of base? Usually a weak base, all right, folks? Now, let's move on. It gives us a Ka value for hyperbromous acid, which is HBRO, and that value is 2.0 times 10 to the negative 9. So once again, we're given a Ka value for an acid, even though we have a solution where we're dealing with a base. So how do we consolidate this? First, I'm going to focus on what is given and what I have. I'm starting with a BRO minus solution amount of 0.400 molar. So I'm going to take that base and mix it with water because it has the ability to react with water. When I take BRO minus and I mix it with water, I get HBRO plus OH minus. Now that I have HBRO, you might be saying, well, okay, well, I have the weak acid here. Can I still use this? No, you cannot. Why? Because what are we actually producing here? We're producing OH minus. Since we're going to get a concentration of OH minus is basic. So we need a Kb value. And the only way to go from a Ka value to a Kb value is to use the expression here. Kw is equal to Ka times Kb. Therefore, our Kb value is going to equal to Kw divided by Ka. So Kb is going to equal to 1.0 times 10 to the negative 14 divided by 2.0 times 10 to the negative 9 because that is the Ka value that's given. When I divide these two numbers, I get 5.0 times 10 to the negative 6 as my Kb value. Now, we have to go back to the question. They want us to calculate pH, but here's the reaction we're working with where we actually get the concentration of OH. So what we need to do is get the concentration of OH minus, then get the POH, then of course move forward to get the pH for this overall solution. All right, so I have to set up my rice table so I can actually solve for the OH minus concentration. I'm starting initially with 0.400 molar of BRO minus. Water doesn't count for us. And then, of course, our products are going to be initially at 0. Now, for the change, it's going to be minus X for our reactants and plus X for our product. And then finally, for equilibrium, I have 0.400 molar minus X. But since our Kb value is small enough, I go ahead and make the assumption up front. And then for our products of HBRO and OH minus, they're simply going to be equilibrium values of X. So as soon as I solve for X, I automatically will have the OH minus concentration, and I can go forward to get the POH and then the pH. So I'm going to take my Kb value, which is equal to 5.0 times 10 to the negative 6, and then I'm going to equal that to my products. When I multiply my products together, that's X squared divided by my reactant, which is 0.400 molar. I have to cross multiply my Kb value from 0.400 molar, and I get 2.0 times 10 to the negative 6. Now, of course, I still have to deal with the X squared, so I need to take the square root of both sides. That's going to leave me with X equaling 1.414 times 10 to the negative 3 molar. Now, this concentration for X is also equal to the concentration of OH minus, and of course, the concentration of the weak acid here. But our focus is OH minus. Now that we have the OH minus concentration, I can calculate the POH, which is negative log of the 1.414 times 10 to the negative 3. And that is going to equal to 2.849485002. And make sure that this is going to be 10 to the negative 3, because for me, it's starting to look a little bit different. This is negative 3 here, all right? Now, we got our POH value. To solve for pH, we're going to take 14.00 minus our POH value. So that's simply 14.00 minus 2.849485002. And my pH ends up being 11.15. And so that is letter D. And for number 19, it states which salt. So of course, we're talking about salt solutions. That means we need to know the cations and anions that come and are a part of these solutions. Depending on the cation and anion, that's going to tell us whether or not it's going to contribute to basicity or acidity, right? So it says which salt is going to react with water, hydrolyzes, to produce a basic solution. What is hydrolyzes? Hydrolyzes means that it's going to break apart with water, okay? That's what hydrolyzing means. And they're saying which salt is going to react with water to break apart to produce a basic solution. So again, we're looking for conjugate bases. We're looking for plain old bases like OH minus, right? And of course, that's all we're looking for this overall question, because they only want basic solution. So to answer this question, you're going to take every single salt that you see here and do the first thing that happens when they get into solution. Disassociate them. And so when you disassociate them into their cations and anions, then we can start questioning those cations and anions. And if they come from strong acids and bases, we know they're going to be spectator. But if they come from weak acids or weak bases, we know that they have the ability to be a conjugate acid or a conjugate base in solution, and thereby cause basicity or acidity. Okay, folks? So let's start with letter A. We have NaC2H3O2. So this is going to disassociate into Na plus and the acetate ion here. C2H3O2 minus. Now the question becomes, does the cation going to cause basicity, or is the anion going to cause basicity? For these two cations here, Na plus is a part of a strong base, so it's definitely going to be spectator. That means we're only looking at C2H3O2 minus, which actually is the conjugate base of the weak acid, which is C2H3O2H, or acetic acid. So since this is the conjugate base, yes, this can cause basicity. Okay, folks, let's continue on to see the rest of them. We have NaNO3, this is Na plus, and this is NO3 minus. Na plus is spectator because it's coming from a strong base. NO3 minus is spectator because it's also coming from a strong acid here. All right, folks, let's look at letter C. We have NH4 plus, and we have Cl minus. Cl minus is spectator because it is coming from a strong acid, and NH4 plus actually is a conjugate acid. Conjugate acid from what base? NH3, or ammonia. So because this is the conjugate acid, it has the ability to cause acidity in solution. Now let's continue on with letter D. We have Ba2 plus and we have SO4 2 minus. Barium or Ba2 plus is coming from a strong base, so it's definitely going to be spectator. And then our sulfate anion is coming from a strong acid, so it also will be spectator. When we're talking about spectators, that means they're not going to react with water in solution, so they do absolutely nothing. That means letter B is going to do absolutely nothing, and letter D is going to do absolutely nothing. So we're down to A and C, okay? Now, the question says which salt reacts to produce a basic solution. So the only one that causes basicity is going to be the acetate ion here, so that is letter A. And finally, for question number 20, it states the weakest of the bases listed is, and it gives us this entire table of all these acids, their conjugate bases, and their Ka values. So they want to know what's the weakest base listed. So what do we know about weak bases? First, we know that they're not strong bases. And why am I saying that first? Is because if I'm going to figure out what's weak or strong, I'm going to memorize one side of it. It's just easier for the brain. I'm going to memorize all my strong bases, and anything outside of it will be considered a weak base, right? But because they give us acids here, we have to go a little bit further. We can't only just think of bases on their own. When it comes with acids, what do we know about them? We know that the acid has the ability to produce a conjugate base. And if you have a very strong acid, it's going to produce the weakest conjugate base. So what we need to do is look at our table and figure out which one's the strongest acid, because guess what? That's automatically going to give us the weakest conjugate base, or simply the weakest base. And that's really the strategy for this question, folks. Again, I'm going to look at my acids here. I automatically in my head already know which one's the strongest one, and that's going to be the one with the greatest Ka value. Or if you already know what a strong acid and strong acid is versus a weak acid, it'll be easy for you to be able to distinguish. Looking at my acids listed, I already know HCl is one of my strong acids. Therefore, Cl minus must be the weakest base. Also, I can verify this because the Ka value is 100%. And so if you have a very, very large Ka value, then you know that you're going to have a strong acid here. So therefore, my weakest base is going to be letter A, which is Cl minus. Yes, we already have our answer. Well, let's go further and figure out which will be the next weakest, okay, or the next weaker conjugate base or base in general. So we have HSO4 minus, H2S, and HS minus. Again, we need to go off of their Ka values. Whichever one has the highest Ka value is going to be the next weaker base of the entire acids listed, okay? So here we have 1.2 times 10 to the negative 2. That means SO4 2 minus is going to be number 2 here. This is number 1. That's cool. And then for HS minus, that's going to be number 3. And then for S2 minus, that is going to be our least weak one. Okay, folks? So they even put Cn minus here, but we could have got rid of that off rip because they didn't even give us that as far as the table goes. All right, folks, that is practice exam number 3. A lot of problems, a lot of questions. It's all going to depend on how much work you're putting in. Do not, and I repeat it, I don't know how many times, do not only rely on the practice exam. With this amount of variables, with this amount of information, there are so many ways that these questions can be given to you. So it's imperative that you understand the concept behind the questions, not just memorize how to do this practice exam problem, because it's going to be more difficult to you when you get on the real exam. So please take heed of my words. Please make sure you are thinking of strategies the best way we can. I hope this helped you. And let's get to it, folks. And practice and reviewing until you get more comfortable. This is going to help you decrease anxiety. Now, this is exam number 3. So guess what? This is going to be the last exam that you can get any type of help with. Okay, so that means for exams 4 and the final, you cannot ask any questions. You have to kind of figure it out on your own. So let this be your chance to make sure you have those strategies and have those tools as you keep going further and further in the course. Now, that does mean I can help you here and there, but if you don't have any information to help me work with you with, then guess what? I will not be able to give you any extra strategies or anything on my own. That means you must make sure that you have a strategy to approach these questions and you practice, practice, practice. And this takes time. So if you are a person who starts the couple days before the exam to start really getting everything organized, you want to make sure you do even more days before the exam because this is 3 chapters, so it does take a lot more work. And of course, do not cheat. The consequence is not worth your entire future. If you do cheat, of course, you go to judicial affairs and you will be blacklisted for up to 10 years in the community college system. You don't want all that. So I recommend that you go ahead and try to strive for these goals of completing the lectures and homework, having a strategy for each type of question, and of course, practice and review, practice and review. Keep repeating this until you get comfortable. And that's it, folks. Now let's get into question number 1.